Hi, and welcome to Homework Help for 5.3, Simplifying Exponential Expressions. We're going to do problems from number 1, 2, and 3 in the homework. So as always, before we get started, we're going to start with a couple of examples that will guide us through the rest of our homework problems. So consider this a quick review. Example 1. I have x cubed times x to the fourth. And I want you to look at example 2 right now as well. I have x cubed to the fourth power. So the number one confusion that kids have at this point is which rule to apply in which situation. So let's remember, when we have the same variable being multiplied by itself with different exponents, this is really what's happening. I have x cubed, that's x times x times x, times x to the fourth. That's 4 more x's. So in total, I have x to the seventh. And so our rule was we're going to add the exponents. That is the shortcut. In example 2, I have x cubed, but I'm multiplying that by itself 4 times. So we have a total of 12 x's. So the answer is x to the 12th. And our rule then is when we're taking a power to another power, we're going to multiply the exponents. So this is from 5.1. It should be reviewed, but it's so important for today's lesson that we are masters of these rules. So when we're taking a power to a power, we're going to multiply the exponents. If I were you, I'd put that in a box, star it, circle it, do what you got to do. Let's go to example 3. Okay, so in example 3, we talked before about how when we have multiple factors being raised to a power, essentially this is what's happening. I'm distributing that exponent to each piece. And so if you look at it, it's actually 2 problems that are just like example 2. I have a power to a power, so we're going to multiply them. So off to the side, I'm going to multiply because I'm not really good at doing fractions in my head. So I'm doing it on the side. I have 6 times 1/3. So I'll put the 6 over 1 and multiply straight across. 6 times 1 is 6 over 3. And that simplifies to 2. So I have x squared. I'm going to put this 7 over 1 as well and do the same process. X squared and then y to the 7 over 3. So notice my x simplified, the y's exponent did not simplify, and that's okay. But wherever you can simplify it, you must. Okay, last example. Here I'm doing a division problem. I have x squared over x to the 5th power. So see if you recall, when we're dividing with the same variable, we're going to subtract our exponents. Here's the visual explanation. I have x times x on top, and I've got 5 x's on the denominator. So we know that 2 of these will cancel, leaving us with x cubed. This, however, would be an incorrect answer. We are left with 3 x's, but we have to note that they're left in the denominator, so you need to leave it as 1 over x cubed. You must put the 1 over, or else it's an incorrect response. For example, 2 and 1 over 2 are different numbers, right? So in the same way, x cubed and 1 over x cubed are very different. Here's the correct answer. If it was, however, x to the 5th over x squared, now when we do our subtraction, we'll do 5 take away 2. We're left with 3 x's, but they're going to be in the top. So that would be x cubed. Okay, with those base skills, let's jump into the homework. Okay, problem number 1c. I have e to the 1/3 divided by e to the 4/3. Here's my hint for this problem. I'm not really comfortable with this division sign because, to be quite honest, I haven't really seen it very much. So I'm going to immediately rewrite that as a fraction. So for instance, if I had 2 divided by 3, that's equivalent to writing 2 over 3. So that fraction sign is like, it just means division. So in the same way, I'm going to write e to the 1/3 over e to the 4/3. And now this looks just like example 4 from our little lesson right now. And so since I'm dividing, we will subtract our exponents. So the way I like to do this is I always take the bigger exponent first minus the smaller, so that I don't have to deal with negative numbers. So I'm doing 4/3 minus 1/3. So recall, when we're subtracting and adding fractions, we do not touch the denominator, only subtract the numerators. So I'll get that's 3/3. So I'm left with e to the 3/3, but that really simplifies to 1. And I'm left with e to the 1 power in the denominator, because that's where the bigger number is. So we don't really have to write e to the 1, it's implied. I'll just write 1 over e. Okay, let's do another. Problem number 1D. Again, it's division, but we should probably rewrite this into fraction exponents so we can use our exponent rules. So I am going to rewrite the numerator as m to the power of some fraction exponent. So have a look. The 3 right here remains my numerator. The power stays on top. But the denominator is supposed to come from the root. There is no number there. And when there's no number, remember that the invisible root is 2 always. So let's put that as a note on the side. So let's write the square root of x. If there's an invisible root, it's the square root. So you're always going to write in the 2 immediately. And if there's an invisible exponent, well, then the invisible exponent is always 1. So if I had square root of x with no numbers anywhere, I would rewrite that as x to the power of 1 over 2, x to the 1/2. This is a super, super famous fraction exponent. So if I were you, I would write it down. X to the 1/2 equals the square root of x, and put a star next to that, put it in a box. You should memorize this. Okay, so coming back, let's fill in our invisible number over here in our denominator. I have m to the 4, and the invisible root is 2, so I'm dealing with m to the 4 over 2. Okay, next step. We have to actually simplify, so we're subtracting now. We'll do the bigger number minus the smaller number. 4 halves take away 3 halves, leaves me with 1/2, and that's m to the 1/2 in the top or in the bottom. So again, we're looking for wherever the bigger exponent was. It's in the denominator, meaning I have 1 over m to the 1/2 in my denominator. So that's a beautiful final answer, but this is also acceptable, 1 over the square root of m, because we know that these are equivalent forms. Okay, moving on to number 2. So what you'll notice here, the only difference is instead of x's and y's, we're dealing with actual numbers. But it's okay, please don't freak out. We're going to do the same rules apply. So if I have 5 to the 2/3 times 5 to the 4/3, let's look back at our mini lesson. Which example did this look most like? Example 1, 2, or 3? Well, this looks the most like example 1 because I have my variable twice and I'm multiplying it. So I should probably use the same rule here and add these exponents. And in fact, 5 to the 2/3 times 5 to the 4/3 will give me 5 to the 6/3. But again, that's not exactly what I'm going to put for my final answer because I can simplify this. So that's going to give me 5 squared. Simplify it more. 5 squared is 25, and that's our final answer. So here's a question that comes up a lot on this problem. Students will say, shouldn't we multiply the 5s and make it like a 25 to the 6/3? And the answer is no. I will show you why right now. Consider this. If I have 5 squared times 5 to the, the third power. Let's see what's really happening. 5 squared means I have 5 times 5, right? 2 times. And I'm multiplying that with 5 times itself 3 times. So if I were to condense this, I'm really dealing with 5 to the 5th power. So notice what we did. Same rules as always. All we did was add our exponents to tell us how many 5s are being multiplied. So our answer is simply 5 to the 5th. We never touched our base. We never did 5 times 5 and got the 25, which is, it looks tempting, I understand, but the same rules as always are going to apply. You just add the exponents. So let's do another one, just a quick one on the side, just to make sure we're okay. If I have, let's say, 15 to the 1/3 times 15 to the 5/3, we're going to add the exponents. 1/3 plus 5/3 leaves me with 6/3. And that can be simplified to 2. So my final answer is going to be not 15 times 15, but just the 15 written once, squared. Since that's an actual number I can compute, I will write my final answer, 225. That's what 15 times 15 is, right? Okay, good. Just checking on my math. All right, next. Number 2D. All right, let's do this problem in 2 different ways because it can be done. There's no one way to do any of these problems, in fact, but I just want to expose you to the 2 ways we can do it. All right, so first, method 1 says when we're multiplying and we have the same base, we add our exponents. So our exponents in this case are 1/2 and -5/2. So that's really 1/2 take away 5/2 leaves me with -4/2, which is -2. So my answer would be 100 to the -2 power. But remember, we don't leave our answers with negative exponents. That negative exponent is going to be rewritten as 1/100 squared. We're going to take the reciprocal. And so finally, 100 squared can be computed. So we'll write our final answer, 1/, it looks like 10,000. You can use your calculator on that. Okay, that's method 1. So we're adding the exponents, and then we have to deal with our negative exponent in the end, and then we're good to go. Let's look at method 2 right now. Actually, I'm going to write it right over here. Method 2. So method 2 would be, let's get rid of that negative exponent immediately. So we're going to take the reciprocal. I'm going to rewrite this as 100 to the 1/2. And instead of multiplying it by 100 to the -5/2, I'm going to bring that 100 to the 5/2 into my denominator. Just like this, over 100 to the 5/2. So negative exponent means, hey, bring that base onto the other side of the fraction sign. So now what I have is a division problem. And I know that when I'm dividing with the same base, I simply subtract my exponents. As we've talked about before, we like to do the bigger number minus the smaller number. We'll get 4/2, which is 2. So I'm left with 100 to the power of 2, not in the numerator, but in the denominator where the bigger number was. So 1/100 squared. Check it out. We're actually at the same spot for method 1 and method 2 right now. Final answer, 1/10,000. So whichever method works for you, as long as you're getting the final answer correct, feel free to continue using that. Okay, last problem, problem number 3. All right, so I'm going to make a quick adjustment on number 3b, it says f of 25a to the fourth f cubed. Since f is actually our function over here, and I don't want to confuse anybody, I'm going to erase that f variable and replace it with a y, okay? Or actually, why don't we do b cubed? Okay, so that's the only change that I'm going to make. Otherwise, we're going to do the same problem. All right, so f of 25a to the fourth b cubed says, I need to plug this stuff right here into my f function. So what I'm really dealing with is 25a to the fourth b cubed to the power of 1/2. Now I want you to stop for a moment and notice how this problem is similar to example 3 from the beginning of our lesson, in that we have multiple factors being taken to the same exponent. And so we're kind of going to distribute that exponent to each piece. So let's look. In this case, I've got the 25, the a to the fourth, and the b cubed. So I'm going to kind of distribute that 1/2 to 3 separate sections. So I can either write 25 to the power of 1/2, or see if this is an easier way of thinking about it. I'm just going to immediately write the square root of 25, because I know that the power of 1/2 means the square root. Now, when it comes to these variables, I'm going to multiply. I have a power taken to a power, so I'm just going to put these over 1 right away and then multiply straight across. So I have a to the 4 over 1 times 1/2, which leaves me with a to the 4 over 2. Yes, I can simplify this in my next step. Let's go to b. I have b to the 3 over 1 times 1 over 2, so that's b to the 3/2. And now in our final step, we'll simplify everything down. Square root of 25 is 5. That will become a squared b to the 3/2. And that's our final answer. So it's not bad at all. Just my only tip is when you're dealing with the number, don't write it as 25 to the 1/2. Just immediately write the square root of 25, because it's easier for us to think about it in that way. Okay, let's look at 3D. So let's plug in negative 64m to the 5n cubed w into our g function. So I'm going to rewrite it. Take it all to the power of 1/3. So have a look. In this case, we're going to distribute that 1/3 exponent to 1, 2, 3, 4 different factors. So let's begin with the negative 64. Since we're dealing with a number, I'm not going to write negative 64 to the 1/3. Instead, I'm immediately going to go cubed root of negative 64. Now our variables, let's fill in that invisible exponent right there. That's w to the 1. And put these all over 1 and multiply. That'll be m to the 5 over 3. N to the 3 over 3, and then w to the 1/3 power. Next step, we're going to simplify as far as we can. So the cubed root of negative 64 is asking what number times itself 3 times will give me negative 64. So that's going to be, I know 4 times 4 times 4 gives me 64. Now I have to think about this negative really carefully. When I'm taking the odd root of a negative number, is it imaginary or is it negative? So let's make some notes off to the side really quick. If I had the square root of negative 9 versus, let's say, the cubed root of negative 8. Let's look up top first. Is there a number that when you multiply it by itself will give me negative 9? Well, it's not going to be positive 3 because 3 times 3 is positive 9. And it's not going to be negative 3 because negative 3 times itself will also give me positive 9. So the square root of a negative number is going to yield an imaginary solution, 3i. But now let's look at the cubed root of negative 8. What number times itself 3 times will give us -8? If you said -2, you're correct. -2 times -2 times -2. Well, these guys multiplied together will give me +4. And when I multiply by that remaining -2, I'll transform back into a negative number. So the rule is, take it down in your notes, the even root of a negative is always imaginary, whereas the odd root of a negative number will simply be a real negative number. So in this case, do we have an even root or an odd root? Well, the cubed root, so that's an odd. So my answer is going to be -4 then. The cubed root of -64 is -4. We can prove it to ourselves down here. That's +16 times -4. It's -64. Let's simplify our variables. M to the 5/3, that does not simplify, so we'll leave it. N to the 3/3, that simplifies to just n to the 1, or just n. And then I'll rewrite w to the 1/3. And that, my friends, is our final answer. Look at all this math that we did. Seriously, I'm like 1, 2, 3, 4, 5, 6 homework problems plus 4 examples. I hope that was helpful. I'll see you next time.